Welcome to this video. Come to think about it, it has been a long time since I last made a video on a computational issue. I have actually made videos on Gnuplot earlier, but there we were talking essentially about the ability of Gnuplot to create two-dimensional plots or fit data from files and so on. In this hopefully short series, I am going to talk primarily about the use of Gnuplot to create something which Gnuplot is not really very well known for, that is, animations. Now, I am pretty sure that Gnuplot is not unique in this respect. Any command line driven plotting program can perhaps be adapted towards creating animations. I know Gnuplot better than any other command line driven plotting program, so I'm going to talk about that. The other upsides of this, of course, is that Gnuplot is a very powerful plotting tool. Not only that, it is free and open source and available for almost all platforms. Now, if you are not very familiar with Gnuplot, you can of course download the software on your computer and use the inline help or read up the help that is available on the net. And as a last resort, you can also refer to my earlier lectures on this particular topic. Let me assure you, it's pretty easy to pick up Gnuplot as a plotting tool. And while learning how to use the command line to control Gnuplot may seem to be rather daunting at the beginning, let me assure you that it's actually quite rewarding in the long run. And frankly, once you get the hang of it, you will wonder what you saw in point and click type of plotting programs in the first place. Now, without much further ado, let us get down to the job of using Gnuplot for animating. But just in case you have forgotten how Gnuplot actually works, let me first show you how it is used to produce standard two-dimensional, that is XY plots. Firstly, in order to run Gnuplot, we need to start the Gnuplot program. For that, the command is Gnuplot, and once you enter that command, you end up with, after some messages that is, a prompt that is actually Gnuplot with an arrow. That is a Gnuplot prompt. This means that Gnuplot is waiting for you to enter a command. Now, a simple command like plot sin x will bring Gnuplot into action, and what you will see is a plot of sin x versus x. Maybe what I will do is I will increase the line width a bit so that it's easier to see. So I will just plot this again, but in addition I will type line width 2, or rather I could just abbreviate line width to LW2. This makes the line twice as wide, as should be obvious. Now you get to see this. The sine curve has been drawn. Note that unless you ask for it, Gnuplot will not plot the horizontal or vertical axis. You have to actually ask for it by saying something like set x-axis or set y-axis. And by default, Gnuplot always plots from -10 to +10. This is a behavior which can of course be changed. The y-axis is automatically scaled to fit all the data. I have already discussed all these in great detail in earlier lectures, so I'm not going to go into the details of that. Also note that there is a key up here telling you what exactly are you plotting. The purple line, in this case the only line, happens to be a line plotting sin x versus x. Just a bit of technicality. What Gnuplot actually does is that by default it picks out 100 numbers between -10 to +10. That's the default range, both endpoints inclusive, and evaluates the function to be plotted at each one of those points and joins the resulting points by straight line segments in order to produce the curve. You can perhaps see the effect out here near the peak here, where you can make out that this does not really look like a smooth curve, but a bit jagged curve has come about. That's basically because you have essentially chosen too few points. If you actually had chosen more points to plot, this would look smoother. You can change the number of points you plotted simply by using a command called set samples. For example, if you say set samples 10,000, Gnuplot will choose 10,000 points between minus 10 to plus 10 or whatever limits you have chosen for that particular graph. Draw each x versus fx point and join them by line segments, thereby producing a much smoother curve than the default 100 points would have. So now let us move on to the issue of Gnuplot scripts. A Gnuplot script is simply a sequence of Gnuplot commands that have been written down in a file. And if you run that file by either using Gnuplot followed by the name of that file from the command line, or by entering a Gnuplot terminal and saying load followed by the name of that file within quotes in this case, the sequence of commands will be executed one after the other. Let me give you an example of a very, very simple and rudimentary Gnuplot script. Here, what we have are 3 lines at the beginning which have hash marks at the front. These are comments. They're ignored by the Gnuplot interpreter. After that comes the actual Gnuplot commands. Set sample 10,000, as I explained a while ago, forces Gnuplot to use 10,000 points instead of the default 100. I have used unset key so that the horizontal line depicting which curve is being plotted does not appear in your graph, just to remove the distraction. And then I've issued a command plot sin x. Obviously sin x will be plotted. The pause command after that makes Gnuplot pause for the number of seconds written down here. So pause 2 means after carrying out this command and plotting the sin x function on the graph, Gnuplot will pause for 2 seconds. After that, it's going to execute the next command, which is plotting sin x plus sin 3x by 3. It's going to pause 2 seconds again. After that, it's going to plot sin x plus sin 3x by 3 plus sin 5x by 5. The final command I've given on this script is pause minus 1. Here the negative pause actually makes Gnuplot wait for somebody to strike a key. Without this, Gnuplot would have just plotted this and immediately exited. As a result, you would not have been able to see the final graph very well. So if you actually ran this program, what you would see is something like this. First, plot sin x will be executed. Of course, set sample 10,000 and unset key will be executed before that, but they don't really show up as graphs on the screen. Plot sin x will show up as this. Note that since the key has been unset, you no longer have a horizontal line up here. We are still using default values. We are plotting from minus 10 to plus 10 for x. And y, once again, has been auto-scaled to fit the entire data in. After 2 seconds, this picture is going to change because you are going to bring in a graph of the next function, which is sin x plus sin 3x by 3. And this is what this function is going to look like. After 2 seconds more, you are going to get this. And by now, even those of you who are not familiar with this, may have recognized what's happening here. We are actually writing down successive sums in a Fourier series for a square wave, and as a result, if you add more and more terms, the resulting sum is going to look more and more like a square wave. Now, admittedly, the way in which we did this, going back to this, by writing down each step one after the other and keeping on adding pauses in between, is really rather crude and rudimentary. And if I wanted to say, add up the Fourier series for the square wave to say 30 terms or 50 terms, that would have been rather awkward being done in this way. So instead of that, what we can actually do is use the loop structure which Gnuplot allows us or has for us. Gnuplot actually has nice ways of summing up a set of series in something called a sum command. It also has a very nice do loop. So I could have actually changed the code above, in fact gone beyond the code above by writing it like this. So do for terms equal to 0:30 means terms will take the values 0, 1, 2, 3 up to 30. So here 0 is the starting value, 30 is the value at which it ends, and the default step size is 1, although you could have said 0:30:2 to ensure that you are getting every second term, or 0:30:m to get every mth term. Now what are you going to do here? You are going to do whatever is within these pair of curly brackets. So you are going to plot, but what are you going to plot? You are going to plot the sum for term going from 0 to terms of sine twice term plus 1 into x by 2 term plus 1. This essentially is a formula which tells you what this Fourier component is, or what the Fourier components are really for the square waves. And in between it's going to pause for 0.5 seconds each. Now if you had this in your Gnuplot script, it's going to plot for terms equal to 0 first, which is it's going to plot from term going from 0 to 0, just one term, and the result is going to be just plot of sine x. Because when term is 0, this simply becomes sine of 1 into x by 1. After sine x is plotted, there will be a pause for 0.5 seconds, then the loop will run again. Terms will now become 1, and thus the sum here will be term going from 0 to 1. Therefore, for term equal to 0, you will get sine x again, but for term equal to 1, you will get sine 3x by 3 added to that. So what will be plotted is sine x plus sine 3x by 3. A further pause of 0.5 seconds, the loop will run again with terms equal to 2 this time. So in the sum, instead of a term going from 0 to 1, as in the last case, term will go from 0 to 2. So one more term, the term corresponding to term equal to 2, that is sine 5x by 5, will be added to what you already had plotted before, and so on. Let us now see this in action. In order to do that, we will return to our Gnuplot prompt, but as we did in the script example before, we will first set the number of samples to a large value, maybe 10,000, and also unset the key. Having done that, I will then type in the command here, one after the other. So just so that we could see both of them together, let me change the size of this a bit. So here, what I will do first is type out do for terms equals 0:30, followed by a further colon and a step size if we wanted to have a step size. Here we don't really want the step size explicitly because the default step size of 1 is fine for us. And then I open a curly brace. Now if I hit enter after that, Gnuplot knows that I have not really completed what I wanted to write. So it's giving me a new kind of prompt, a continuation prompt, which in the case of Gnuplot says more, rather obviously, followed by the angle sign. So the next line goes here, plot sum term going from, that is term equal to 0 to terms of the summand in this case sine 2 star term plus 1 times x by 2 into term plus 1. Now, after this, we have pause of 0.5 seconds and follow this by a closing curly bracket. Once I hit the enter with this, Gnuplot knows that I have entered the full command and is going to give us the output. Let us see what the output looks like. This is what the output looks like on your screen. As you see, after every 0.5 seconds, the number of terms being added up is increasing. And you would notice that something rather strange is happening. Strange, that is, if you have not seen this before. Note that what you really should have is a square wave. And of course, as you're adding more and more terms, it's getting closer and closer to the square wave. It's not getting any closer now, if you have noticed carefully, simply because all the 30 terms that we wanted to add it for have been added. And what you see here is something which will persist even when you add more and more terms. This spike that you see here, etc. happens every time you're trying to use Fourier series to sum up a discontinuous function. This is called the Gibbs phenomenon, and the mathematical explanation for this is really not very trivial and can open the door to a lot of questions and discussions. Of course, what you also see is that there are wiggles where there should be a flat top, but the wiggles are getting smaller in amplitude as you add more and more terms, and in the limit, those wiggles will go away. What will not go away are the spikes that you see at the position of the discontinuities. I hope you are convinced by now that Gnuplot can allow you to use rather high-end programming tools like for loops and so on, and using that you can create simple animations of the kind that you have just seen. However, I personally find the for loop a bit cumbersome to use, especially for writing more complicated animations. More complicated, that is, than these animations that I've just shown you. And I really love a feature of Gnuplot which makes writing loops like this very, very easy. This is the reread function. And the way that works is the following. When Gnuplot encounters the reread command in a script, it simply loads the script once again. So let me show you a very, very simple example of a script which uses the reread function. The script runs as follows. It's stored in a file which is called easywave.plt. For ready reference, the name of the file is also put in the script, but as a comment. It also tells you as a comment that what it's supposed to do is supposed to plot a running or a traveling wave. And the way this works is simply this. You are simply plotting the function sine of x minus ct. Ct here is really not c times t, it's just a variable which is called ct, but is supposed to invoke in your minds the idea about speed of the wave into time. Then it's pausing the plot, the script for a period of time given by this variable called sp. After that, you update the value of ct by adding sp to this. Now you have a slightly larger value of ct, and as long as this ct is less than 5, that's what the if ct less than 5 is telling you, it rereads the script. So the script gets loaded again, but now with a slightly larger value of ct, and therefore the graph will actually shift slightly to the right. But you should realize that this is really nothing but a plot of a traveling wave with k equal to 1. The typical formula that we use for a traveling wave is sine of k into x minus ct, where c is the velocity of the wave. And here we have just chosen k to be simply equal to 1. Now, how do I run the script? Of course, I first write the script out in a file. And that is what I've already done. If you will allow me, this easywave.plt is in a file. I'm just using the vim editor, the vi improved editor, to show you the result. But you can write it using any text editor you want, or manipulate it or edit it using any other text editor you want. It has to be a text editor, remember, not a word processor like Word. In Windows, Notepad would do. WordPad can introduce special characters. It's best to avoid that. Word, definitely not. So these are the contents of the file. And because Vim happens to be aware of these scripting languages, it is actually giving you some kind of help using colors. For example, the two lines at the top are clearly seen as comment lines from the fact that they are being typed out in a different color. Now, what happens if I try running this program? Now, there are two ways of running a script, as I've already said. One would be simply to go back to the command line and type Gnuplot followed by the name of the script, in this case easywave.plt. So let's see what happens when we try that. Now, as many of you may have already guessed, what is going to happen when I try this out is simply that I'm going to get an error. The error comes in because Gnuplot does not know what the value of this variable ct is. In fact, it's pausing or stopping rather at the very first error. It doesn't know what ct is, neither does it know what sp is. You might even argue that it does not know what x is, but remember, by default, unless otherwise mentioned in the plot command itself, Gnuplot always takes x to run from -10 to +10 and takes the values of x just by using the number of samples it needs to take between that interval. So x is known to Gnuplot, but ct is not, neither is sp. So the one way of running this would be to go to the Gnuplot terminal, supply to Gnuplot the values of ct. Let's say ct is 0 to begin with. That is, I'm just starting at 0 time. If you think of ct as c times the time. Put sp at some small value. This sp is the amount by which ct changes every time. So the smaller it is, the slower time will flow. The larger it is, the faster time will flow. You'll get bigger shifts. So let's take a small value of sp, let's say 0.05. And then I want to run the program, the script easywave.plt from within Gnuplot. For that, what we have to do is say load. Load is the command, which of course I've also seen before. But and once I do that, this is what you're going to get on the screen. I hope it's visible. It's a running wave which runs. Now it has stopped running simply because ct has reached 5. So let me just show you this once again, just to make sure that you can see this. Note that ct has already reached a value of 5 now. So if I had tried to load this again, it would simply not run again because the loop will not run. I have to reset ct to 0, which is easy to do. You just use arrow keys to get back your earlier commands and then load easywave.plt. And now you can clearly see the wave running. So this is a very simple traveling wave animation, and it can be quite useful to demonstrate what traveling waves really look like, what the equation actually means, by showing students this on the screen. If you're a teacher, you can convince your students that a traveling wave really does travel. Now, another way in which this easywave.plt could have been called is by using another script. I prefer calling this other script with an init prefix. So I will name this init wave.plt. Now, inside this script, all I will do is write down the commands that Gnuplot needs to run this. One thing I could do at the beginning is put in the set samples command at a larger value than 100. This is just to make the curve look a bit smoother. And then we will put CT equals 0.0, SP equals 0.05 or any other value. You could play around with these values, especially the value of SP, to see how that affects the motion of the wave on your screen. And after you have done that, I'll just ask this script to load easywave.plt. Now we are done. We all have two files now, easywave.plt, which actually does the plotting, and initwave.plt, which does the initialization stuff. And now that you have this initwave, what you can simply do is call initwave.plt using Gnuplot. So running the initwave.plt script, which at its very end has its load easywave.plt script after supplying the necessary initializations. So when you do that, the script is going to run smoothly from the very beginning. Of course, once the 5 seconds are over, or CT reaches 5, actually, the job of this program is done. Once the script ends, the graph also vanishes. Now, is this all you can do with the Gnuplot animation? Of course not. You can do much cleverer stuff. Now, I can't really explain all of it in one video. So, I will just, as a sort of advertisement for the next video, show you the kind of animation that could be written. I'm not going to show you the script today. Remember, it's a teaser basically for the next video. I'm going to just let you think about how you could possibly write that animation. In the next video, we will explain in detail how that works. This is wave motion once again, but the line that you see in purple, the main curve that you see here, is actually not a single monochromatic wave with a single wavelength. It has a bunch of waves put together. And notice the peak here is actually traveling faster than the major component wave, which is shown in this light cyan in the background. If you follow the peak, you will see the peak is actually jumping apparently from one of these to another. That is simply because it's moving faster, twice as fast. Now this was for a special kind of wave packet called a Gaussian wave packet. Let me just show you how you could change the program just a little bit and change this to a so-called Lorentzian wave packet, which looks slightly different, but the overall lesson will be the same. We will talk about the details of this in the next video as promised. But for the time being, just take a look at what this is going to look like. So once again, you have a wave packet which actually is much more sharper, but you can see that the peak actually is traveling on to the next peak, apparently jumping from one peak to another of the background wave, but that's basically because it's traveling faster. The packet as a whole, or rather the peak of the packet, is traveling faster than the main component itself. Here you have an example of a situation where the group velocity is double the phase velocity. You can easily change the code here to take a look at what happens when the group velocity is equal to the phase velocity, in which case, as you may have guessed, the whole packet will travel without actually showing any distortion. You could also have special situations where the group velocity vanishes or even becomes negative. So although the whole thing is moving forward, the peak actually travels backwards. Now, exactly what does that mean is very easy to figure out from the animation, which you can easily get by just changing a few parameters in this particular program. We will discuss this in the next lecture. Goodbye for today.